Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from Scratch in Go, where we using this book but writing everything with the Golang. And in the previous video, I started to implement optimizers. So we start to implement the stochastic gradient descent optimizer based on the what's called learning rate decay. We achieved some results, but it's definitely not the best optimizer, so we're going to the next one. Today we'll start from the stochastic gradient descent with momentum, and we will go further in the book. Also, I noticed that, this small scrolling bar, it's getting closer to the middle of the book, which is interesting. Okay, so stochastic gradient descent with momentum. Momentum creates a rolling average of gradients over some number of updates and uses this average with the unique gradient each step. Another way of understanding this is to imagine a ball going down a hill. Even if it finds a small hole or hill, momentum will let it go straight through it towards a lower minimum, the bottom of the hill. This can help in case where you're stuck in some local minimum, bouncing back and forth. With momentum, a model is more likely to pass through local minimums, further decreasing the loss. And remember that our goal is to decrease the loss, meaning that teach the model be more correct in the predictions. Simply put, momentum may still point towards the global gradient descent direction. Recall the situation from the beginning of this chapter, so we have this start and it kind of stuck in the first local minimum, because ideally it should find this one, but it's stuck here. With regular updates, stochastic gradient descent optimizer might determine that the next best step is one that keeps the model in a local minimum. Remember that the gradient points towards the current steepest loss ascent for that step, taking the negative of the gradient. So this step might decrease loss for that update, but might not get out of the local minimum. So we will decrease it here and here, but it's the local minimum. We might wind up with the gradient that points in one direction and then the opposite direction in the next update. So we will go back and forth, but still in a local one. Pointing in the opposite direction. The next update, the gradient could continue to bounce back and forth around the local minimum like this, keeping the optimization of loss stuck. Instead, momentum uses the previous update's direction to influence the next update direction, minimizing the chance of bouncing around and getting stuck. Recall another example shown in this chapter, so we continue to go on the hill, even if it's locally it feels like it's not optimizing, but eventually we'll end up in the global minimum. We utilize momentum by setting the parameter between 0 and 1, representing the fraction of the previous parameter update to retain, and subtracting, adding the negative, our actual gradient multiplied by the learning rate, like before from it. The update contains a portion of gradient from preceding steps as our momentum, and only a portion of the current gradient. Once again, the update contains a portion of the gradient from the previous steps as our momentum and only a portion of the current gradient, so it's a mix of the gradients updates. Together, these portions form the actual change to our parameters, and the bigger the role that momentum takes in the update, the slower the update can change the direction. When we set momentum fraction too high, the model might stop learning at all, since the direction of the updates won't be able to follow the global gradient descent. I mean, I guess it will just continue to go. The code for this is as follows. So we have the weights updates. We have the momentum value, which is, I think, the parameter between 0 and 1. We have the weight momentums from the layer. So we take in a fraction of this, and then we subtract the current learning rate multiplied. So we have the weights momentums and the derivative value respectively to weights multiplied by the current. So this is the old approach, right? Well, more or less. Yes, so we have the d weights, we minus it with the current learning rate, then we adjust the weights. But here we add in this portion. The hyperparameter self-momentum is chosen at the start, and the layer weights momentum starts as all zeros but are altered during the training as weight momentum equals to weight updates. Okay. This means that momentum is always the previous update to the parameter. So it says the previous change. We'll perform the same operation as the above with biases. We can then update our HDD optimizers classes update params method with the momentum calculation, applying with the parameters and retaining them for the next step as an alternative chain of operation to our code. So this is why the first one should be zeros, right? The difference is that we only calculate the updates and we add these updates with the common code. The difference is that we only calculate the updates and we add these updates with the common. So if we use momentum, if layer doesn't contain momentum rates, create them filled with zeros, build vanilla HDD parameters. So this is called vanilla. Okay, update weights and biases using either vanilla or momentum updates. Okay, so that will be update, weight, and biases, right? This is what's called vanilla HDD, right? And if self.momentum, so I think it should be, so we still have the, okay, so that's the mix. So we still have the learning rate decay, and let's show an example to how adding momentum changes the learning process. Keep the same start learning rate and decay. Okay, let me change it. Have the same. By the way, can I write and go like this? Okay, yeah. And using momentum of 0.5, and momentum should be a part of the optimizer. Okay. Okay, so let's implement a couple of things. First, I need to change the layer. Layer should have, I think it will fall into this group. Okay. Actually, I'm not sure if I need to. Do I need to create it as a math that it's as a dance from the GoNum or just standard? Okay, what do? We initialize, then we'll use weight momentum. So we will have the multiplication, current learning rate, again multiplication, and then we will have the subtraction between. Okay, so I think it should better to have it as a math dance. We weight momentums, that will be math dance again. Biases, bias, momentums, math dance. Okay, we are going to use it. Where are we going to use it? Used by optimizer. Then we need to have momentum as float. I mean, I will use float 64 everywhere, but for example, for these values, the smaller float. Do I have the on-site float? No, I don't. What it means, I need to have the momentum here, right? And we have momentum equals to momentum. Surprise, surprise. Right, so that means here it will be half. This way, catch. I don't need this. Okay. What do you don't like? Oh. Anything else? Oh. No, 1e minus 3. This is the run model, but I'm using the second one, this one, testing. Right? So we have the momentum. Then we let's actually here I still need to have a copy, and then we deciding if optimizer momentum is bigger than 0, then we implement in momentum, right? Else we implement in the vanilla HDD, right? So what we're going to do first, we need to check if the layer weight momentum equal to nil. That means that I need to allocate. It means that I need to create it for the first time. That will be, I think I have the same What was? I think I can make the dense copy of the layer, dense copy of layer weights, right? This one. Then I can do weights momentum, I think 0. And then I'm doing the same for bias. Right? Biases and bias momentums 0. New allocate. Okay. It should be done once. Yeah, so here, because it's a Python, is a dynamic language, we could add properties dynamically, and then we kind of here we're changing if this property was added, well, wasn't added before, it means that it doesn't exist. In my case, I need to create it before, well, I mean the variable, and then I can allocate it. Okay. Weights updates and the bias updates, basically this is, I need to change this one, right? So where it's used. Okay. Let's rename it so it won't confuse me. Weights. Oh my god, weights dates. Yes. Yes. Oh no. Once again, I'm changing the due weights for weight updates, and yes, no, yes. Then the same I'm doing with this one. We have the biases, and that will be bias updates, and again G is for the global search and C for confirmations. For example, here I want to change then, well, unfortunately it covers it, but then I don't want to replace. Here I want to replace want, okay. And biases. Okay, that should work. Okay. Oh, right. I'm curious. Okay. Works. Okay, so we have the weights update and bias update. Then we need to and we actually will store them. All right. I'm curious. So the first thing we implement in the weights update. Okay, just weights. Since I cannot write it in such way, you know, like in one line. I will need some temporary variable here. I'm just checking how many things I can reuse. Or actually, I can write it in one apply method, right? How it will look like. So I will have wait updates. I will have apply that takes function, and then it too many return values. No. Right. So what we want to return? We're taking the optimizer momentum multiplied by weights momentum layer weights momentum at ing, then minus self-calling rate, that's current learning rate from the optimizer multiplied by layer d weights ing. Okay, so this is the weights update, and then we want to store it as momentum. Then I need to do the same for the biases, right? So this is biases, and so this is bias updates, and then we're taking the momentum, we're taking not the weights but bias momentum, then we're taking the optimizer current learning rate and the biases, and then we assign bias momentum to what we just calculated, right? That's it. Okay, make our full HDT optimizer class. So let's take a look. We have the pre-update, which is the same. We're checking if we have a decay param, meaning that we're changing the current learning rate over steps. Then we have update params based on if we're using the momentum or not. If we're using the momentum, then we need to create arrays for for the first time, because we actually need it only for in case we're using the momentum. And then we're calculating the weights updates as momentum multiplied by the weights momentum, so that will be from the previous iteration, because for the first iteration that will be 0, because we just created it as zeros. And the first step will be actually the same. Yeah, it will be the same as the vanilla stochastic gradient descent. I'm just checking measure current linear rate multiplied by the d weights and the specific place. So here that's the V. I don't use the... Yeah, we'll just calculate in this one. So, but here... I mean, we could take, for example, here the B from here, but it's actually, for me, it's easier to read, but this one is a little bit faster because here I will need to index, but it's, well, since it's one-dimensional array under the hood, it's pretty fast. Okay, let's show an example illustrating how adding momentum changes the learning process. Keep the same start learning rate 1 and decay from the previous training attempt and using a momentum of 0.5. So we have it. Okay, we'll use the same number of the epochs. Okay, so dimension mismatch. Nice. Dense arithmetic. In 15. What do you mean? How is that possible? Dense arithmetic. That's odd. Lie. I mean, I'm calling the apply method. How is... Wait. Did I miss something? So it takes the copy. Oh, it's... Okay, let's change it, but it should not... It should not make a difference. So the vanilla will be weights update is -1 multiplied by layer d weights at I and j, and same here, layer multiplied by d bias at I and j. Oh, okay. I found the issue, but I mean, okay, that's okay if I I forgot to change one param, but let's take a look if it's the refactoring that I did is doesn't break the vanilla one. Okay, it's not broken. Okay, then yeah, I here forgot to change the, because I mean this is really kind of still confuses me. The apply method takes the input not from the object that was, from which one you call it, but it actually returns the result into this variable and takes this as an input. So I forgot to change this one. This is why that was a mismatch, which makes sense. So we got very good accuracy and pretty small loss, right? Nice. The model achieved the lowest loss and the high accuracy we have done so far, but can we do even better? Sure we can. Let's try to set momentum to 0.9. Really? That will make... This is a decent enough example of how momentum can prove useful. Okay, let's take a look. Loss is 0.33, accuracy is 0. I mean, I still have random weights. Interesting that for my values, well, yeah, in that case, it would be much better to have, one, not to actually using the random values, because, I mean, in my case, yeah, for example, for this set of the initial weights, this is like very good result, and I just rerun a couple of times. And I mean, this one is really good, but it's actually interesting how the randomizing the parameters makes such a big difference on the result. Okay. This is a decent enough example of how momentum can prove useful. The model achieved an accuracy of almost 80% in the first 1000 epochs and improved further, ending with the accuracy of 93.3 and the loss to this. These results are a great improvement. The HDG optimizer with the momentum is usually one of the two main choices for an optimizer in practice next to Adam optimizer, which we'll talk about shortly. First, we have two optimizers to talk about. The next modification to stochastic gradient descent is the AdaGrad. Okay, we can go. AdaGrad, short for adaptive gradient, institutes a per parameter learning rate rather than a globally shared rate. So, per parameter learning rate. So we have different set of the learning rates. I mean, different learning rate for each param. The idea here is to normalize updates made to the features. During the training process, some weights can rise significantly, while others tend to not change by much. It is usually better for weights to not rise too high compared to the other weights, and we'll talk about this with regularization technique. AdaGrad provides a way to normalize parameter updates by keeping a history of the previous updates, so we kind of accumulate or use it somehow. The bigger the sum of updates is in either direction, positive and negative, the smaller updates are made further in training. So I guess the goal of this is to prevent one specific, parameter take, major portion of the values. This lets less frequently update parameters to keep up with changes. effectively utilizing more neurons for training. The concept of adding grade can be contained in the following two lines of code. Cache, parameters gradient squared, param updates, learning rate multiplied by the parameters gradient divided by the square root from the cache plus some epsilon value. The cache holds a history of squared gradients, and the param updates is a function of the learning rate multiplied by the gradient, basic. Okay. And then is divided by the square root of the cache plus some epsilon value. The division operation performed with a constantly rising cache might also cause the learning rate to stall as updates become smaller with the time due to the monotonic nature of updates. That's why the optimizer is not widely used except for some specific application. That's why this optimizer is not widely used. Constraint cost. So with the time it will have less impact. Epsilon is a hyperparameter pertaining control knob setting, preventing division by zeros. I think we have the same. I think we had the same with here when we calculated the current learning rate. The epsilon value is usually a small value, such as, yeah, it's pretty big or pretty small one, which will be defaulting to. You might also notice that we are summing the squared values only to calculate the square root later, which might look counterintuitive as to why we do this. We're adding squared values and taking the square root, which is not the same as just adding the value. For example, the resulting cache value grows slower and in a different way, taking care of negative numbers, because if we put a negative number in the power of 2, it will become positive. The result cache value grows slower in a different way, taking care of the negative numbers. We want not to divide the update by the negative number and flip its sign. Overall, the impact in the learning rates for parameters with small gradients are decreased slowly, while the parameters with the larger gradients have their learning rates decreased faster. Okay, so for example, we have one parameter that grows very fast. Then with this technique, we will slow down this growth, and on the countryside, okay, on the other hand, if there is a parameter that did not, didn't have enough attention, like this, and didn't grow that much, so these parameters changes will grow faster. To implement ADA, but I'm not sure, do we need to implement it? Okay, it's separate. Okay, then I will implement it because it's a separate class, since I don't want to mess with the stochastic gradient descent one. To implement that, we'll start by copying and pasting our SGD optimizer, changing the name, adding a property for epsilon with the default of this value to the init parameter and removing the momentum. Next, inside update params method will represent momentum with the code. Okay, what we're going to do. Add a goal, right? So this is the optimizer. Yes, I wanted to save changes. Then we go into this one. We copy everything that we have, and then we change it. So this will be the optimizer Adam, right? And here we have the same new Adam. Then we change it. So we have the optimizer SGD, and we changed it for the optimizer Adam. Yes. Okay. Then we don't need the momentum, but instead we need the epsilon, which will be the float again, right? That means we changing the epsilon to be epsilon value. Surprise. And we will make it here. Okay. Then we have weights cache. Well, I don't like, basically this is the same. From the SGD optimizer, but I don't like that I have to create used by SGD optimizer, right? And then used by other optimizer, but it will not be momentums, it will be cache, as they call it. Okay, so we're going to do the same. That will be our results, right? This is a little bit different, but I will still do the weights updates. Okay, so we're removing the code for the optimizer. I think I will clean up all of this. Why? And then we're checking if we have the weights cache equals to nil, then we do the same. So this is the weights cache, again cache, that's bias cache, and bias cache, and yeah, copying the weights and the biases again. Then update cache with the squared current gradients, and we need to add the value, right? Okay, so what we doing? We taking the weight layer, weight cache, again apply, so this is the function, and we taking the layer deweights, and what we're doing with, we need to append. So since we need to append, we taking the weight cache, and our B will be the previous value. Then we add in layer dot deweights at ing squared. Cannot do this. Okay. Do I have something like math power? Okay. That will be math, come on, math power and 2. Let's take a look. So we're taking the previous value from the history. This is the v. Then we're taking the current change after the pass. We are squaring it, and I need to do the same for. I need to do the same for bias cache. Deep bias, no. Deep add. I should not change. I should not forget to change this one. Oh no. Again, same mistake. Layer. Bias cache. Okay. What it means, then I can calculate the weights update and what it will be. So I have the weights update, again apply. Since I'm using the weights update as a temporary object, I don't need to use v, right? But what I'm doing, and I'm calculating the weights update will be this plus equal sign for the layer.weights. So what we need to return the difference, which is -1 multiplied by the optimizer current learning rate, yes, multiplied by the layer d value at I and j, divided by square value plus optimizer, not this one, epsilon. But I need to calculate the square value. So layer weights cache sum sub scales scale multiplies the elements of by f. But I think I can okay dash skirt there from the numpy. This one returns the non-negative square roots of array element twice. But I think it should be the number, right? only thing that bothers me is that the numpy returns a non-negative square root of an array element 5, so and it returns in the array. An array of the same shape as x containing the positive square root of each element x. In any element x is complex, a complex array is returned, and the square roots of negative reals calculated. So okay. So we add in more and more. Okay, so we square in. Okay, so every element contains the history of more and more and more. And then we are taking the square. Okay, so it's actually not the one. It means here I need to take math as squared from what? Layer, weight, cache, at ing. Okay, so optimizer current learning rate multiplied by the current d weights divided by square root from the history of the previous change in power of 2 plus epsilon, and we put it into the weights update. So I need to do the same for biases, bias updates, then here it's debiases, right? Then we have the bias cache, debias. And here it's bias updates. Okay, so that looks like, is it? This is the optimizer now with the decay set to -2 as well as the -4. Wait. Where is it? We added the cache and its updates and then dividing the updates by the square root of the cache, full code of the other optimizer. Okay. Test with the optimizer now with the decay set to as well. It looks better than this one, which we have used previously. This optimizer with our datasets works better with less decay. Okay, so we have the adegrat decay. So I'm going to change it, right? So instead of SGD, I'm going to have new other, and new other contains learning rate. One decay was set to this one, and the last is epsilon, which should be, I think, -7, right? Yes. Then we run model training without optimized, so it has high accuracy and small loss value. Let's see. Well, again, it fully depends on the initial params, but I wouldn't say it's actually better. I mean, this current version. Okay, so we have 90% of the accuracy. But for the current data set, I think it's less than. So this is with the other optimizer 0.84, but SGD with this one, yeah. So it's actually worse, right? But I think this is just an intermediate step. Adequate works quite well here, but not as good as the SGD with the momentum, and we can see that laws consistently fail throughout the entire training process. It's interesting to note that the Adequate initially took a few more epochs to reach similar results to stochastic gradient descent with the momentum. RMS prop. I think this is the next one, right? I'm just checking the recording time. Okay. Continue with the stochastic gradient descent adaptation. We reach RMS prop, short for root mean square propagation similar to undergrad. This prop calculates an adaptive learning rate per parameter. It's just calculated in a different way with the undergrad. Okay, so we're going to implement another optimizer, and we'll end up with, the several optimizers. We'll continue tomorrow, this one. So thank you for watching. I will push the code to the GitHub a little bit later, but it should be available with this one and with the previous video once this video is published. Thank you for watching, and I see you tomorrow. Bye bye.